Hey, AP Chem. We are moving into Unit 7 now, finally. It seems like it's been a long time with thermodynamics because it has. But we're going to be getting into what we call chemical kinetics. And even though our title here says reaction mechanisms, which is what we're going to actually focus on today, the big kind of umbrella for this unit is something called chemical kinetics. And it is something that you've probably never really seen or talked about before in your regular chemistry classes. So this should be something kind of entirely new to you. And it's kind of unique. And I would say there's something kind of oddly enjoyable about it, but maybe that's just me. So I just want to give you kind of a real brief introduction to the kinetics concepts, and then we'll get into mechanisms in just a minute. So when we talk about reaction kinetics look at how fast a chemical reaction happens, and it's what we call the rate of the reaction. We're going to do a deep dive into rates in our next video, but in general, the rate is just how fast that chemical process happens. In kinetics, we also take a look at how changing the amount of reactant that we have changes how fast the chemical reaction occurs at, which is a whole segment of math that we're going to take a look at. And this is kind of what we're getting into today, is what steps have to happen to create a chemical process. So to get from reactants to products, how does that happen in the first place? And so that's what we're going to kind of take a look at today with mechanisms. So the first thing that we need to talk about today is something called collision theory. And it is essentially what has to happen for a chemical reaction to occur, because there are some things that have to happen. If they don't, the reaction's not going to occur in the first place. So the first thing is that your reactants need to hit each other. And we've talked about this a lot, that I'm going to attempt to use these colored light up ball things here. This could go horrifically wrong, so I guess bear with me. Okay, so we'll imagine that these are two sets of reactants. They are identical. I've got kind of this is purple, but I think it looks white in the light, and then a green ball, and then I've got another purple and green ball. So if you think about this as a sample of particles, they are moving around. And if I want a chemical reaction to happen, the first thing that needs to happen is these guys need to hit each other. So they need to smash into each other and collide. The next thing that has to happen is when they hit each other, they have to have sufficient energy to break apart in the first place. And that ties into our activation energy that we talked about with our stuff in the previous unit. So they have to have enough energy so that when I hit them, the force that occurs with this collision is enough to break this bond here. Okay, so the bond between these guys needs to be broken with sufficient force from the collision. And they need to have the proper orientation. And what I mean by that is that these particles need to hit in a way that's conducive for that process. So let's say, and I've got a graphic coming up, but I'm going to kind of walk you through it first with these. Let's say in my reaction, I start off with one purple or one white and one green together. So we'll call this AB and AB. And in my chemical reaction, I have it making A2 and B2. So it's AB plus AB makes A2 and B2. So when they hit, the proper orientation means that the right stuff is touching to make those connections happen. So if I want A, we'll call these purpley, you can't really see they're purple. These white guys here, okay, and these green guys, they have to hit in a way that the new things that form touch and have sufficient energy to kind of snap the bonds and reform. So in this particular combination, I could have my two molecules hit this way. And if they hit, these purple guys could stick together and these green guys could stick together and they could split. And that could happen. That's a correct orientation. Another correct orientation could happen if we hit it purple to purple this way, kind of head on, and then it breaks apart these bonds here, and then somehow these green guys find each other and they reconnect, okay? Or we could have a process where maybe, like I said, I'm not the most coordinated. So these guys hit and we lose one green guy, and then the lone green guy comes in and hits that way, okay? The one type of collision that's not going to work, though, is going to be this one, where I have these two hitting, because if they hit green to purple, that connection isn't going to yield a purple to purple and green to green connection. So orientation is important. And you're going to see a picture here where you're like, why didn't you just do that? But we're going to take a look at these anyways. So the same thing happens here, where I have 2NOBr, and that turns into 2NO and Br2. So they can hit side to side, and that will yield a Br to Br connection. They could hit end to end, and that will yield a Br-Br bond. But if we hit O to O, that is not going to be a successful collision, because it's not going to connect kind of in the way we want it to. So when we talk about our collisions, they need to collide in the correct way, and they need to collide with enough energy. So if we go back, they have to hit each other with enough energy and in the right orientation, or the reaction isn't going to happen. So what ends up happening, though, is that step that I kind of showed you. Sometimes we always imagine in our heads that it happens all at one time. Like we just smash everything together and then whoop, everything magically turns into its product. But that's not the case. Sometimes what we need to do is we actually need to look at the individual steps that make that happen. And a lot of times they predict that it's actually a series of collisions that have to happen. And when you think about that, it's kind of a wonder that stuff even turns into product successfully. And that's one of the reasons, if all of our steps of our reactions have to happen step by step, why we sometimes don't have 100% yield, because a lot of things need to go right to get us all the way from A to B. And what ends up happening is that the steps that we predict happen to get us from A to B are called reaction mechanisms. So it's a proposed series of steps for a chemical reaction. A mechanism, and this is kind of the weird thing about it, is mostly a theoretical thing at this point. It is hard to prove that a mechanism is something that definitively exists. But what ends up happening is that a mechanism can be considered, quote unquote, plausible, because it's supported by experimentation and the lab data supports that this can happen. And when I get into the terminology, I'll explain to you why it's really difficult to prove. Mostly it has to do with the fact that we can't trace individual atoms because they're so tiny, and it's often difficult to prove that these things exist the way they do. And like I said, I'll trace back to that in just a minute. Okay. So when you look at a mechanism, what it's going to look like is multiple steps of a chemical reaction. And they kind of go together like a Hess's law problem, where you take all of your stuff and you combine them and cancel out things on both sides. And we'll take a look at them. Each of those individual steps is called an elementary step. And they behave a little bit different than a balanced equation normally does. And we will circle back to that in a different lesson. So here is what a mechanism needs to have in an elementary step. An elementary step needs to show, or I'm sorry, a mechanism needs to show the specific order that the bonds break and reform. So this happens first, then this happens, then this happens. The mechanism includes something called an intermediate. So an intermediate is it's not quite like an activated complex, but it's in the same neighborhood as that. And so an intermediate is a stable molecule instead of an activated complex that's unstable, that is created as a product in one step of a mechanism, but then you use it up in another mechanism. So it's kind of like a temporary molecule that exists to get you from A to B in your mechanism steps. And all of your mechanisms contain a slow step called the rate determining step. So if you think about a slow step, it's like when you're driving on the highway and all of a sudden the car lanes go down, right? You go down and like the cars are all backed up and you don't know why. It's because we all have to kind of go down to traffic to 2 lanes. That is the rate determining step on your trip, because that's the narrowest part. And that's the part in our mechanism that slows down our reaction. So it's written as the slow step or the rate determining step. Like I said, this is like a big Hess's law problem. So the elementary steps need to add up to give the overall balanced equation, and your Hess skills will come into play at that point. And this is the big thing, and how they can say that a rate law is, or a rate mechanism is plausible, is that the rate law, which we will get into, not today, but soon enough, The rate law for the rate determining step must match with the experimental rate law. So that basically means that your theory has to match with the data. And it does a lot, and it's kind of cool how it works. Okay, a couple more terms before we get into actual mechanism stuff. When we talk about elementary steps get one of three different names. They are either called unimolecular, and unimolecular steps are when you have one, because uni means one molecule as a reactant that breaks apart into multiple things. So if there's only one reactant, that elementary step is called a unimolecular step. If there are two reactants in an elementary step or a step of your mechanism, it's called a bimolecular reaction. And if it has three different things, it's called a termolecular elementary step. Now, termolecular elementary steps are rare because it means that three particles all at one time have to collide, correct orientation, correct speed, correct energy, all that stuff. And they're very, very rare. So you don't see them very often, and it's difficult to make happen. And what ends up happening, just as a note for you guys, is that in a bimolecular reaction or a termolecular reaction, the things that are your reactants can be the same. And like I said, it's a little bit different than what you see in a reaction. So you could have an O2 and an O2 colliding together, and you would write it as O2 and O2 most of the time. Okay. So I think the best way to kind of dig into this is to take a look at a mechanism. So this is a proposed mechanism for a reaction. And so in this particular setup here, there are three steps that they are saying happens. So if you look at this first step here, they are saying that two NO collide together. So that's kind of like my amazing ball trick here. So two NO are hitting together. Because there's two NO hitting, that makes this elementary step here, this is our first elementary step, that makes that first step bimolecular. And what they do is when they hit, they propose that all of them stick together and make this thing called N2O2 here. Okay? Then, in the second elementary step, which is marked as our slow step, so we're going to call that our rate determining step, in our second step, that N2O2 here is used up because it hits together with an H2 and makes N2O and water. So what happens is hydrogen collides with this molecule, and then it takes an O and makes N2O and H2O. The next step of the mechanism then suggests that this new N2O here gets together with another hydrogen that's floating around, and it turns into N2 and H2O. Okay, so again, you have to think about this as a sequence of events. The first reaction has to happen, then the second reaction happens, and then the third reaction happens. So it's kind of like following like a series of reactions that happen. And that's different than a normal Hess's law problem where we've just got kind of random things put together. So this is like following a series of steps that we will go through. And we'll take a look at a graph of that in just a second. So some things to keep in mind. When we set up our process here, if we want to find the overall reaction from the series of mechanism steps, you play the Hess's law game. So we cancel out things that are identical and add things that are the same on both sides. So if we look at this reaction, we can cancel out the N2O2, that's gone, and then we cancel out the N2Os. And what we get in the end is 2NO right here, plus 2 hydrogen, and that turns into N2 and 2H2O. So this mechanism at the top here is a proposed series of events that give me this overall reaction. So this mechanism says it takes 3 different steps to make this process happen. All these collisions have to occur to get from start to finish. In this case, the stuff that I canceled out, if you notice, I'm going to kind of go backwards for just a second. I produce something, and then immediately in the next step, it gets used up. N2O is the same thing. It's made, and then it's used up. And it does not show up in that balanced equation. If that's the case, that is what we call an intermediate. So things that are made and then get consumed right away are intermediates. In this particular reaction, we don't have a catalyst, but a catalyst looks like this. A catalyst is something that I put in as a reactant, and then it participates in my chemical reaction process, but then at the end, it pops back out. And that's the cool thing about a catalyst. A catalyst, when you put it in, you should, in theory, get the same amount of stuff back out. So a catalyst in this case, like I said, there's none in this reaction, but a catalyst would go in as a reactant and then come out as a product. And our rate determining step is the slow step, like I said, so it's our second step. Okay. Now, we can tie this together with a graph, like an energy diagram that explains it as well. So this is that same mechanism drawn as a 3-part reaction. So if you think about our normal energy diagram, I would draw this as a big starting line and a big hump here, and then it would go down and we would end lower in energy, meaning this is an exothermic process. However, a mechanism includes little bumps here for each step in our process. And what happens is you generally, when you draw a graph like this, have your starting and finishing areas in the correct location. So if this would have been endothermic, I would have ended higher. And then I cannot imagine a world where they're going to have you like draw the exact energy changes for each of these. But because there's 3 steps, we have 3 humps on our graph here. This is the first energy step, the second, and the third. And you might notice on here that the second one has the biggest activation energy. And what happens is our slow step is always the one with the biggest activation energy. So from this kind of intermediate position up to the activated complex, that is the activation energy for that step. It's always biggest in our slow step. So if our slow step would have been first, I would have a big activation energy here and then a smaller one as we go along. So just kind of keep that in mind. Okay. We are going to be at the beginning of this taking a look at mechanisms, identifying parts to it, and all that kind of jazz. Now, if you remember back from when we talked about energy diagrams, we talked a little bit about catalysts. And catalysts, we talked about how they shave the activation energy off. So if this were a catalyst that I'm adding here with this purple line, it would make the bump of this a little bit lower so more molecules could kind of get over the bump. When you add a catalyst, the catalyst needs to go into the slow step. Otherwise, it doesn't matter. So if you think about your traffic reference again, if I've got a highway that has 4 lanes, okay, and my slow step is the 2 lanes that it goes down to because of construction. If after I go through the construction, I have 8 lanes of traffic available afterwards, it's not going to matter because it's still going to take the slowest part to get people through the 2 lanes of traffic. So a catalyst is only really successful in speeding up a chemical reaction if it affects the slow step. If you add a catalyst and it participates in a process that's fast, it doesn't really do anything. Okay, so this is kind of our first glance at mechanisms. We're going to get back into mechanisms after we go through all of the kinetics math, and then we'll take a look at them again, tied together with the math that we know now. So if you find yourself having any questions, get those things cleared up. Otherwise, good luck.